More and more of the front rows are becoming just mine.
Yeah, great. Yeah, I think more of you should sit in the front rows because you can see better, no?
Yeah.
But yeah, I don't know.
And it's easier to ask questions.
Yes.
You can tell when I don't understand.
Exactly. So, 1 second. Can anyone hear on Zoom? I see some yeses, great. Oh, 1 second. I have to. 102. The screen help. I was going to say that the screen helps me see what people on Zoom see, so I know things work. Yeah, okay. So hello everyone. Sorry for the late start. Everyone can hear me well on the back as well, and on Zoom, I hope. Yeah, do write if you cannot hear me on Zoom. Do let me know. Write in the chat. So we discussed last time about expectation maximization and how we can use we can develop a clustering method that is much more sophisticated. It can take into account, as opposed to k-means, it can take into account also the variation in the cluster, like how elongated it is in the particular directions. We had the probabilistic assignments of vertices to clusters. We had all these very nice properties. And just to recap a bit, the idea was that our goal was to find the parameters of each of these clusters. We had a red cluster, a green, and a blue. Let me see why this doesn't work. Of course, because I haven't connected it. 1 second. Yeah. So we had this setting where we had 3 clusters: a red one, a blue, and a green, and we have to find the parameters for the Gaussian distributions corresponding to each of these clusters, as well as these thetas, which are the prior probabilities that we sample data from a particular cluster. So the prior probability that, or let's say put it otherwise, what percentage of the data is contained in the red cluster? Maybe 20% is contained in the red cluster. Maybe 60% in the green one. It's a bigger cluster, let's say. This is what theta represents. And we saw how we can split this into 2 sub-problems. And this is, I really want to get, like, there's 2 key concepts here in EM, and it's how we fit these with these parameters and how we split into 2 sub-problems. So I want to make sure you understand this. So we split into 2 sub-problems. The problem 1 is, if we knew the assignments of the points to clusters, how do we find the parameters of the Gaussian distributions, per se, of the clusters? If we knew the assignments, if you knew which points are red, which points are green and blue, how do we find the parameters of those distributions? That's the problem number 1. And problem number 2 is, if we knew the parameters of our clusters, red, green, and blue, then how do we find the assignments of the points to the clusters? That's problem number 2. So it's a chicken and egg problem. It's the same chicken and egg problem as we had for k-means, where we had the same type of updates. We first updated the centers of the clusters, and then we updated the allocations of points to clusters, and we solved them iteratively. So this is what we went through last time, and we saw how if we do, for example, for the first problem, if we knew the cluster assignments, how do we find the parameters? We saw how we can actually get these analytical updates. We basically get closed form solutions for each of these parameters, theta, mu, and sigma. But I wanted to stress, because we get closed form solutions for this particular case, which has a mixture of Gaussians, but it's not always the case that we get closed form solutions. For some more sophisticated models, we might not get. And I'll show you actually I'll spend the first half of the class today to show you a real problem, like application, how we used EM in my previous lab and to analyze brain imaging data. And I'll show you right now very shortly. And we'll see how in some of those cases we did not get closed form updates as we have here. We don't get analytical solutions right away because they're more complex models, and for which you don't get such solutions. But we do have here in this setting, we do get closed form updates. And for the second problem, if we knew the parameters, find the cluster assignments, again we end up getting, 1 second. Here, so we end up getting again closed form updates, where we basically these are the allocations of point n, data point n to cluster k has a closed form update, which is like this, which is a theta k times the likelihood with respect to that particular cluster k, and we put this all together in this algorithm where we initially initialize the parameters to some values. And then, so this is the first 4 or 5 lines. Don't look in too much into this, but we just initialize the parameters. And then we have 2 steps. We have an E step and an M step. And in the E step, we find this allocation. We compute these variables. So for each data point n, for each cluster k, we find what's the assignment of, what's the probabilistic assignment of data point n to cluster k, according to this likelihood. So this is, and you see this is the exponential from the Gaussian distribution, this is the normalization constant from the Gaussian distribution, and this is the fraction theta. We normalize we compute also the ZNs, like for where we sum over all the possible k's, And then for each cluster, we find their parameters, the mu's, the sigmas, and even the fractions, theta k. Any clarifications, any questions? Yes.
In the previous slides, you had in parentheses hard and soft written. So what is the difference?
Yeah. So soft inference is when we. No, hard inference is when you fully allocate a point to a cluster, like the entirety of the point of the data point to a cluster. A soft assignment is when you say, oh, this data point is like 20% comes from the green cluster, 60% from the blue cluster, and the rest from the other cluster. So it's this soft assignment. You don't make a hard choice decision that this data point belongs to only one and only cluster. That's what soft means. Any other questions? I know it's not an easy algorithm, but here's a chance to get clarifications. Yeah. Any questions from Zoom? From the Zoom participants? You can unmute yourself and ask. Okay.
So
Yeah.
on the compute step, so what, maybe you said this, but I don't really get it. What exactly is happening here?
Yeah. So we, in this step, what we're doing is we're deciding, intuitively we're deciding which colors the points are. If you remember, we had that diagram with colored points. We kind of reassign the colors. That's what we do. We have those particular colors, like for all the clusters, and we reassign them. We update the coloring of each data point in this step. And once you have a coloring, you know which ones are the red points, which ones are the green points. Then you can fit the cluster. You know all the green points you fit, and that's what you do in the M step. Does it make sense intuitively? You know, we update the colors for each point here, then we fit the distributions only to the colored ones. Yeah. And if you remember in k-means, we had a hard assignment. Here we have a soft assignment. So in some sense, all the points have some for example, let's say the green cluster. When we update the green cluster, all the points have some component of green in them. Maybe some have very little, like maybe 1%, but some yeah. But you do a weighted average. That's why when you do these, you see you update the mean of the green cluster. You do a weighted average of all the data points and weighted by the green component. Let's say the z measuring the green component, how green they are. Yeah. Okay, so let me show you now in the first half until the break. I wanted to show you a real practical application of how we actually use the expectation maximization to model brain imaging data in Alzheimer's patients. Is that okay? Like, would you be interested? Yeah. So just to show, I think it's very nice, and it shows you just how powerful it is. How you can apply to solve real problems, and you can fit much more sophisticated models, not just mixtures of Gaussians. So it's not this one. Yes. So I've taken this from my PhD thesis. And you can find it on my website and also online. This is taken from my website. So let me go up. Yes. So this is what the project was called. Was building a spatio-temporal progression model. So so for the progression model, what it means, it's a model of disease progression. It was measuring how diseases progress over time. Like, for example, in the case of Alzheimer's disease, how it progresses over many years. So it sometimes takes 10, 15, 20 years for such a disease to progress in people and actually develop really severe symptoms. Spatiotemporal means that we were modeling changes both over the space, over the brain regions, spatially, so frontal lobe, occipital lobe, and so on, and also temporally over time. So it was taking into account both space and time, and it was, of course, it was modeling brain pathology. So and in neurodegenerative diseases like Alzheimer's disease, which is a type of neurodegenerative diseases, but there's many others. Many other diseases that are not like Alzheimer's. So let me show you this diagram, which I think is key. So basically, basically what we have here. Actually, I'll do this. I'll do it from here. So what we have is a set of brain images. We had a collection of many brain images, brain MRI images from many patients with Alzheimer's disease. And our goal was to find which regions in the brain were affected. And you see them here with red. So the red regions are very affected by the disease. And for example, the blue ones are not so affected. So the model could basically tell us what parts of the brain were affected by the disease. The first thing. And the way it was doing that, and of course, so you have, we had a total of 1,500 brain scans to fit the model. So there was quite a large, and each brain scan had, it was a 3D brain image, so had around 200 by 150 by something by 100 voxels, 3D pixels. So you're talking about almost also like 1 million voxels in an image, basically, that you had in the raw MRI scan. So what we were doing in this model was that we were considering that the brain was made up of, was created by many points. We got this brain surface like this, which was measuring disease signal at each point. So it was made up of many points, many locations on the brain, and at each location we could measure brain disease pathology. And the way it was measured was by measuring the thickness of the cortex, how thick the cortex was. And over time, the cortex would get thinner and thinner because the gray matter was dying. So, but the idea is at each point in the brain, on the brain, we could measure disease. And then what we were doing, we were grouping the points into clusters. We were doing a clustering method that was clustering these points based on the trajectory dynamics. And what we mean by this is that the clustering was, we were modeling a trajectory that showed how the cortex was getting thinner over time. So, for example, this means high cortical thickness, and it was getting lower and lower over time. And these are measurements, for example, at that particular location on the brain for a particular person, for a particular patient. So we were clustering. So see here, we were clustering temporal trajectories, not just individual data points here. It's an entire trajectory. So the idea is we had like multiple trajectories. For example, like all of these lines are individual trajectories. All of these on the right side. These lines are individual trajectories from many points on the brain, and we were clustering them based on similarity. So, for example, we were trying to fit 3 clusters: a red, green, and blue, and Yes, and then sort of like trying to characterize that. And what we would get essentially is when we fit these three clusters, we get, for example, 3 different colors on the brain here. Now we have 4 or 5 in this particular image, but the idea was that we get we can see which points are red, which points are green, for example, and which ones are blue, and that meant severely affected, medium, or not severely affected. Does that make sense? Yeah. So and of course, you first, when you do something like this, you have to first define the model. What is the model that you generate? So in the first, these few equations, we were basically creating. In our case, this was the Gaussian mixture model, what we had in the slides. But here, the model was much more complicated. We were assuming that given a particular age, this is the Tij is the age of subject I at a clinical visit J. And we were estimating a disease score S, and this is a linear transformation of the age. And alpha is the progression speed. It shows how fast the subject would progress, and beta is kind of like a time shift, showing when the disease started in the particular patient, like 5 years ago or 10 years ago, for example. And we ended up building. Trajectory. So now we were defining a trajectory for each point on the brain. So a trajectory, this trajectory for each point on the brain image. And you see this has a sigmoidal shape, and this is how we defined it. We defined it with a function which is a sigmoidal function which has this particular expression, and we call that f. And then we were defining a noise model, a Gaussian noise model around the value of this particular sigmoidal function, showing how, showing that in practice you can have measurement noise when you try to measure the cortical thickness at a particular location. So this is what we have here. This is the age of the subject. Alpha t plus beta now gives us the disease score. F of disease score gave us the thickness of the cortex at that particular location, and then we assume a measurement noise around that value, and we do this kind of approach. We extend it to all the subjects I at all clinical visits J. So because a subject can come 3 times to the hospital or maybe 4 times, so you do that multiple times, and we assume, you see. When you see the product, it means what does it mean we did here? What assumption have we made? I know it's a bit loud, but can you hear me? So what assumption do we make when we assume we factorize like this with a product over multiple people, over multiple like independence? Yes. So we assume that these joint distributions, because this is like the data set for all locations on the brain, for location L on the brain, but for all the subjects I, and we assume that this is independent for each subject. So each subject is independent with each other. So they're actually independent observations. When do you think this will be violated in medicine? When subjects are independent? When this assumption will be violated? Yeah. What if they're family members? Yeah. Heritage, yeah. In what sense? Yeah. So they, if they're family members, they share same genetic makeup. So then they might. So for example, for many of these diseases are actually heritable diseases, especially like Alzheimer's. So if you have some particular genes, there's 3 known genes, PSEN1, PSEN2, for example, that are familiar. So if your parent had them, you will, and if you inherited them from your parent, then you will also get the disease. So they're not independent. So basically, so sometimes this will be violated. This assumption of independence, because you are related to the data point which comes from your parent, for example, or someone else. But just I think it's great. It's actually great. These are great answers, all great answers. So it's great to be aware of these kinds of limitations. And then we did the same for, we extended this model to all the vertices on the brain, all the locations on the brain, because so far we were talking about only one location, L, on the brain. So one, if we go back to the diagram, here we're talking about only one location here, one location on the brain. We extended to all the locations. And again, if we do this, again, we assume again independence across all locations. We assume this factorizable form. And the reason again we do this in practice is because it becomes if you don't assume this, it becomes highly intractable. Highly intractable. You have to model correlations across brain points and so on. Although we later on we extended the model to also include to model spatial correlation. But let's find out why. So what happens if you assume independence across points on the brain surface? What can mess up in the algorithm? So let me go to this. What would happen if we assume independence across brain locations?
So when those locations very close, they can be highly correlated.
Exactly. Let me repeat. So when the locations are very close, they can be highly correlated. It's like imagine a photograph, 2 pixels next to each other. If one pixel is red, the pixel next to it is also likely to be red. It's highly likely to be red. So they're very correlated, the pixels next to each other. Same for this approach. Like if we take a point here in the middle of this blue cluster, it's highly likely that the point next to it will also be blue, will be in the blue cluster. So we want to model that spatial correlation somehow. And we modeled it with these, they call the clique terms. You basically assume it is like these points that are adjacent to each other are basically correlated. So then you, if they have the same labels, if 2 adjacent points have the same label k, so if they equal, then you reward that term. Otherwise, you penalize it. You do a minus, a negative, or something else. So you multiply with either with the positive or with the negative. So you either reward it or you discourage it. If they're different, if the classes are different. So, but the key step here is that we're trying to find. We have these latent variables z that, as exactly in our setup with the Gaussian mixture models, now they show which point belongs to which cluster. They're trying to find the allocations of points to clusters. But here, the data points, remember, these are locations on the brain. So we're trying to find which location on the brain belongs to a blue, which one to red and green, and so on. So these are the latent variables that we will use, and we can use expectation maximization to fit this model. And let me hide this. Do we have messages in the chat? Yes, that's correct. And, so how do we use expectation maximization here? So first of all, let me show you a bit of data set. So look, 1,973 subjects times 160,000 vertices. So this is the size of the data set. We're looking at the table. And again, whenever we apply expectation maximization, we have to derive 2 steps. One is the E step and one is the M step. And they both start from the same kind of expression. So So of course in the E step we try to find the values of the latent variables z, And in the M step, which I'm going through here, we try to maximize the parameters of the model. So we try to find the maximum parameters that maximize the expected value. So you see what you have here is you sum over all the latent z of p of z, and what this means, this is the expected value over something, and it's expected value with respect to z over the log likelihood, the full log likelihood of the model. So remember in EM what what we had to do was to do expected value over z of log p of z. So p of what? What was here actually? So we do expected value over the latent variable z of something, of a log likelihood. What's that log likelihood? And x as well, I heard. X being what? Our yeah, but it's good. It's good. What was x?
X is the data point.
Yes, the whole data set, not just a single data point. The whole data set. Yes. So we have the data set x, and we have the latent variable z, given something. What was given what? Yeah? Theta. What was theta? Prior parameters, yeah. And what other parameters did we have? Mu and sigma, yes. If it's a covariance, but if it's a variance, it's a small sigma. Or a small sigma. Exactly. So remember this. We always do this in EM. We compute the expected value with respect to z of this. And let me make it a bit more clear here what this means. So this is more exactly, what is this z? P, it's like the posterior of z given what? It's P of z given something. So what we do in the E step? This is the E step here. What do we compute here? P of z given what? Theta. Yeah. Let's first start with the data, right? Because before we include the parameters. So z given x, and what else? Theta. I had the theta. Yes, so that's a parameter. What about these ones? Do we include them? What do you mean by model? Model parameters? These are the model parameters, all three of them, yeah, exactly. Let me change that to a small sigma, just so I don't confuse. Because, just so we're still in the unidimensional case for now, we're not in multivariate yet. So, but it's still a vector because we have multiple clusters. Yeah. Now there's something special about these versus these ones. Can anyone tell me? Let me move also. I'll let you think about it. What's special about these parameters versus these ones? Any ideas? So what remember? So what do we do in the E step? We find the value of the assignments of data points to clusters. This is the Z given the parameters of the model from the previous iteration, right? So if we denote the iterations, like this will be from the previous iteration. So this will be from iteration u minus 1. This will be from iteration u minus 1, u minus 1. Yeah, and then we find new parameters for the current iteration. So now we do an argmax of over theta, mu, and sigma of this whole expression, and these I hope you can see, but these are theta, mu, and sigma at current iteration u now. At u and also at u. So these come in here. So I estimate a set of new parameters at iteration u as a maximization over this whole thing. So this is where they optimized here. So these parameters bound to these ones, given a set of, but this distribution is computed with these parameters added from the previous iteration. Anyone who doesn't understand or still have questions? Okay, so let's see. So what we did here, given so I hope you understand this. Does it make sense? Okay, you have a question.
Why the reason plus and not PM is
Yeah, that's a prior over these parameters. You can add a prior there, so you can actually what you can actually do. Is you can even, instead of this, you can even put a full joint, p of z, x. So instead of bar, I put a comma here. So or let me do this instead. Instead of given this, I take this out, I delete, and I put a comma, and now that becomes a joint distribution over all the 5 variables. And when you do that, you still condition it. You have zx given that times the prior of those. So that's what this prior m are the model parameters here. You see in this case, alpha in that case it was alpha, beta, theta, sigma, and lambda. So this way you can have an EM algorithm that also has priors on the parameters, and you use Bayesian formulation this way. So notice this exact form. Look at this. So we estimate the current parameters at iteration u here as the maximization over all the model parameters over the expected value over the latent variable z given the parameters from the previous iteration, the E step. This is the E step here. The same as here, this part. And then we have the log likelihood of the complete model, now including complete meaning including the latent variable z. Just as here. So this is the case for our Gaussian mixture model we had before, and this is the same for this more complex model, but it's the same approach. So So this is what we're saying here. So in the E step, we estimate P of Z given the parameters from the previous iteration from U minus 1. And of course, and this is, and you do the derivation. So you do the derivation of this, and you compute this posterior. So you factorize over all the regions of the brain, over all the patients in the data set, and also include spatial smoothness. And yeah, you can write it like this. I'm not going to go into too many details on this, but you end up with a formula for ZLK. So this is again the assignment of particular point L to a cluster K. And you have and I gave you the full derivation for this particular setting. So so it ends up being again the product over all subjects I and J of the log likelihood for each subject, and here we this product is over only considering cluster K. You see the parameters theta and sigma only for cluster K, because we're computing the contribution to cluster K here, ZLK, of location L to cluster K. And again, we have this term just models spatial smoothness. So just to have that, but in a more simplified form, you can even take that out, so you won't have this other type, this other form. And of course, it's much easier to compute the log of it because then you can break these products apart, and that's where they get summations. And you end up with this final form, which looks like this. So it has a data term, which has the Gaussian distribution. So you see this is the Gaussian distribution, exponential. This is the normalization constant of the Gaussian distribution, and this is again the spatial smoothness term, but now with the log form. So that's how, for example, we derive for this much more complicated model the E step. So you just have to compute here the posterior probability P of Z given this. This is the E step, and you derive it. So then we did the same thing for the M step, and here for the M step, what we were computing was the shape of the trajectories, and also the time shifts of the subjects, alpha and beta. So what these meant, if I go back to that diagram, well, it will take a while to load. Do I have it here? Maybe these slides. I'll give it a few seconds for that to load, but the idea is, for example, when this was optimizing the shape of the trajectory of the evolution of the thinning of the cortex, how the cortex gets thinner and thinner as a sigmoidal function. So here what we want in the M step. So now in the M step, and we have to find the maximum over these parameters. Now we computed this. So this is where we're at here, and we start, for example, with theta, which are which are not these theta actually. These thetas are the shape of the sigmoidal in this particular case, of that sigmoidal function. But again, you do the maximum over theta, argmax, just as here, argmax over theta, over the expected value over z of the log likelihood of the complete model. And you write it out. One of the first things we do is that we break this apart. This is a joint posterior over all the variables. You break your seam independence, and you break it into all multiple z1s and z2s. Exactly here, we assume that ZL is conditionally independent from the other vertices, Simon ZM. So this is so here we broke it into multiple. We assume independence between ZLs, and we took the log by now. So now since we took a log, the product became summations. and we reach this form, and now we simply have looked here. So we have the likelihood is in terms of like these normal distributions given of VL given the mean. So now instead of a mu, we have the shape of that sigmoidal function f and sigma. And we simply expand the Gaussian noise model. So we write it out. What is the Gaussian noise model for this n? It's this. It's the normalization constant times the exponential. And because this is a log, it's a log of the normal distribution. And constants disappear. And eventually we get this final update rule. So we get an update rule for theta, which looks quite different from what we had. So what is happening here is that we cannot, for example, simplify this further, and we still have to do a maximization of theta. So as opposed to, so this is what I was trying to explain a bit earlier, as opposed to the Gaussian mixture model where we get analytical solutions. Sometimes in these steps, like here, we did not get analytical solution. So you see, we cannot simplify this further. And the reason is because we have a function f here. That is that sigmoidal function. And maybe for the sigmoidal function it might work, but if you change and do something else, it might not work in general. So so normally how you would optimize this analytically is that you take the derivative of this function with respect to theta. But again, and this would assume that you can pass the derivative through this function f here to get to theta. Remember, we see how theta is inside the function. So so if you can do that, then yes, you can perhaps derive a closed form analytical solution if you can solve that system of equations. And you do the same for all the other parameters, also for the measurement noise and also the time shifts. Again, you do an argmax over all these. Well, actually, I want to show something interesting for the measurement noise sigma of the Gaussian distribution. So these sigmas. So for this one, we actually do get a closed form solution. So after we reach this form, but for this one, we actually can take the maximum of the derivative. We take the derivative of the function. We set it to 0 eventually. Well, after we simplify it a lot, so this is where you kind of like pass the derivative inside the function. You simplify all terms. You set it to 0 to find the first order conditions, and then you get a closed form update for sigma. And this is so for this particular parameter, you can get a closed form update, but not for this one. Do we have any questions? Yeah.
Background question, is there any influence on like the medical treatment on the patient will have an influence on the because you take the time into your consideration. In this case, will influence your measurement or bring some new noise.
Are you saying if there's a medical treatment that we can take into account? In the model, you mean in the model? Yeah. So first of all, the unfortunate situation is that for these diseases, we do not have any medical treatments at the moment that work. So for Alzheimer's disease, there's no curative treatments, and unfortunately, we're actually quite far away from even having one because we don't understand what is actually happening in the brain. So I've been to several Alzheimer's conferences, and it's quite a sad situation actually. Like there's so much we still do not understand about the brain. It's like we have a puzzle, and we have so many gaps and missing pieces in what is actually. There's some theories about how there's this like toxic protein called amyloid that somehow misfolds and ends up creating a cascade of bad events, like, oh, the amyloid misfolds, then it starts aggregating into these bundles, and then those bundles start depositing on the myelin sheath of the axons, and the myelin sheath gets disrupted, this gets destroyed between neurons. If the myelin sheath gets destroyed, then the neurons cannot signal and fire towards each other, and they start dying. When the neurons start dying, then you have atrophy and so on. And eventually, you have a cognitive impairment. So it's all it's a sort of, and we don't a sort of many events that we do not fully understand. So we still don't have treatments for it. So yeah. Yeah.
In the algorithm itself,
Yeah.
like how many iterations do we use? Like how do we set the number of iterations usually?
Generally, this is more empirical. There's no theory on this. You let it run until you see that it's sort of converged. You can define some criterion like the parameters, for example, the difference between parameters at iteration u minus 1 and u is less than a threshold, for example. It's something like they can define that, but that threshold will be, in practice, quite sensitive to your data set. So it's it's more empirical. It's kind of like when you see, for example, in this particular scenario, it's quite easy. When you see the clusters stop changing in the brain, that's when and I don't have videos to show you how, but essentially what happens over iterations is that, and finally it loaded, because I can show you the diagram again, so I don't have to jump through it. Here. So these clusters over the brain, so initially you start with an allocation that is bad, and over time, over iterations, they will change. You see that you can visualize them changing and changing and changing up until they kind of stop, and they sort of converge. So And for example, if you try to model other kinds of diseases, you will see it froze. Oh, 1 sec. Here. Look at these clusters. Look, for example, actually look at this versus that. Look, you see, so this is a different type of modality called a PET imaging, and you see how this toxic protein aggregated in this region and that region a lot, and here we found an optimal number of 20 clusters, for example, would fit this, and you see these gradients kind of that were estimated. So depending on the data set, you would have completely different also patterns of clusters, and maybe convergence might be longer also. Any other questions? Any questions on Zoom? Okay. Yes, so I wanted to see if there's something. One final thing I wanted to show you is how, do you remember the AIC and BIC criterions? We touched briefly, like at the end of the K-means lecture, we were saying how we can use these criterions to optimize the number of clusters K that we fit in, because the K is a hyperparameter. And the same problem we had in our case, we did not know how many clusters we had in the brain imaging data. So for example, we use AIC and BIC to estimate that hyperparameter to help us find an optimal hyperparameter. And here is, for example, the true number of clusters. This is a simulation, so we need the true number of clusters. And this is the estimated one. And you see how when we simulated data from 2 clusters or 10 clusters or 30, these AIC criteria would give you very close. Yeah, they would give you almost the true number of clusters optimal that was found. So notice the diagonal is the perfect estimate, but they are very close to the diagonal. That's another example. So how you can use these criterions AIC and BIC to optimize your hyperparameter K of the number of clusters.
So in this case, is AIC a better measurement?
It was better, yeah. It was closer to the true. You see, it's closer to the true, number of clusters than the BIC, at least for these higher ones, yes. But in general, I don't know. Maybe so what I'm trying to say, maybe for a different problem, maybe the BIC might be better. That I don't know for sure. It depends on the problem. But at least in our study here, it was, BIC was a bit better. Any remarks, questions? Okay, why don't we take a break? Let's take 8-minute break, and we'll resume afterwards. And we'll do boosting. So in this lecture, we're talking about boosting methods. And boosting methods are very, very nice, very interesting in ML. They are ways to make a weak classifier better. So if you have a classifier that is weak, for example, a simple linear regression, a decision tree with one single node, something like that, you can make it much better by doing these boosting methods. And the idea is that you don't use a single one, you use an ensemble of them. Like for example, you combine 100 different linear regression models together. And basically when you combine multiple of them, like 100 different linear regressions or 100 different simple decision trees or 100 different other weak classifiers, then your prediction improves. I think so. This is an idea that is sort of called the wisdom of the crowds, and it was. I don't remember all the details. For example, there's one story that I wanted to briefly mention about. So there was a study that somebody did, and I forgot who, but an early nature study in 100 years ago, more than 100 years ago, 1903, something like that. It was someone went to random people to ask about prices of a particular product. You have a particular product and you ask random people on the street, what's the price of something? I forgot exactly what was the object. And when you ask someone, for example, someone might overestimate the price, someone might underestimate the price, someone else might underestimate the price. But you ask many people, many people, like you ask 200 people, for example, like that. And the result was that the average of all those price estimates from 200 people, even though each single one was very much off, the average of all of them, or the median of it, was very close to the true price. So there's something, so what that meant is that there was something probably like, when you put together all those predictions, there's something, it's a lot of performance improvement you make. So there's maybe some kind of wisdom in the whole crowd that is still there. It's just not every single individual person has it. But when you combine everything together, then you get a much better. So for example, in that case, a much better price estimate of that particular product when you ask that many people. So even though every single one of them underestimates or overestimates. So that's the idea of using ensembles of groups of hypotheses or groups of models together to improve the performance. And you can get different hypotheses by using different data. You can use different, so you train on different data sets. Like for example, you have a data set and you split it into chunks, and then you train on the same model on chunk 1, chunk 2, and so on. Or you can also use different algorithms. For example, you can train a neural net or an SVM or a linear regression model or a decision tree or any of that, and you put them all together. And you can even try with different hyperparameters. So you try, for example, the same, for example, k-means, but you try with different values of k, and you ensemble them all together. So that's the idea of ensembling. So the idea is that, again, and in general, that averaging does reduce variance because the ensemble is generally more stable than individual predictions. So, and you can see this by considering an example of a biased coin. So, for example, if the bias of the coin is 1/3, the probability of having a head is 1/3. If we compute the variance of the number of heads, and let's see what that turns out to. So the variance, remember, the formula of the variance is this. For the number of heads is E of h minus E of h squared. That's the formula, and it can be also rewritten as this: E of h squared minus E of h squared. So, this one is the mean squared, so which is just 1/3 squared, and that one is something different. If you compute it for a single flip, you get this. For example, you get 1/3 minus 1/9, and if you do the calculations, and I'll let you do that at home, but basically you get, for one flip, you get 2/9, and you end up with a value of 2/9. But when you do the average of two flips, if you do 2 flips, and you take the average number of heads in 2 flips, it drops to 1/9. So the idea is that the average over 2 flips is smaller than the average for a single flip. So then when you average these two events together. Yeah? And of course, if you do that over n flips, like if you do multiple flips like that, then the variance divides by n. So the variance decreases. And this is also like a result that is also called the law of large numbers, and it's related to the central limit theorem in statistics, although that one is actually much more general than this. So, and the big assumption here is that the flips have to be independent. Again, this wouldn't work unless we make this assumption. One second. Because I wanted to do an exercise, and I wanted to see if we do it here or if we do it a few slides below. Let's do it now. Let's do a quick exercise on the board. So. Move this again. So imagine you have 3 classifiers, F1, F2, F3. So you have 3 models. F1, F2, F3. And each of them has a 20% chance of making a mistake. So each of them 30% chance of mistake. Sorry, 20%, not 20. So then, and the performance of so obviously the performance of each one of them is of each is 80%. Now, what happens if we do majority voting on these 3 classifiers? Like, what if we have 3 these functions F3, and now we do majority vote? So we do a majority voting. Let's see. So you have F1, F2, F3. So there's so when do you make a mistake if you do majority vote? So each of them will make a mistake. So this is a binary yes or no, for example, setting. So for example, if the first one was correct, the second one was correct, and the third one was wrong, then we made a mistake. Then this is correct, right? This will be a correct prediction. So if the first one is correct, the second one is wrong, third correct, this is also going to be a correct prediction. We also have this. First one is wrong. And in what other case do we get also correct prediction?
All of them are correct?
All of them are correct, yes. So we have a fourth case when all of them are correct. So if we compute what's the probability of this event happening? The first correct, second correct, the third wrong. So its probability of correct is 0.8, 80%. So this is like this. So 20% chance of mistake, so 80% correct. So this is 0.8 times 0.8 times 0.2, which gives 0.128. Same for here, 0.128. Yeah, it's the same, just flipped. This one also has chance 0.128. And this one is it also 0.128? No. How much is it?
0.8 times 0.8 times 0.8.
Yeah, so it's 0.8 to the third. So it's 0.512, I think. Yeah. So the idea is then if you sum these up, 0.52 plus 0.128 plus 0.128 plus that, we
Probability that the ensemble is correct.
that's in general the probability that the ensemble is correct, because these are all the 4 cases when the ensemble is correct. Yeah? Does it make sense? These are all the only cases where the whole ensemble would be correct with majority voting. And the probability that the whole ensemble is correct is the sum of all of those. So it's 0.512 plus 0.128 times 3, because we have 3 of these. And this gives us 0.89%. So no percent, no, well, 89%. 0.89.
So if we had calculated it in the other way around and said calculated the chance that the ensemble was wrong, would that end up adding up to 0.11?
Yeah, yeah.
The chance that it was
Yes,
wrong?
yes, yes. So if you do the other way around, it will give the same. But notice how now this is higher than this. 0.89 is higher than 0.8, than 80%.
Is there a case where this isn't true? So if everyone is like a coin flip, like the 50-50%
Yeah.
chance of being right, nothing is what anything change with the ensemble's chances of being right?
Say that again. I didn't get it.
So if their chance of being correct is 50%,
The chances of being correct is 50%.
and then like we did the same thing, would any of the values change? Would they have a higher chance still of being correct?
Yes, yes, yes. The same would happen. Yeah. For any probability between 0 and 1, even if it's 0.1. So even if this was the performance of each independently was 0.1 or like 10% or even 5%, this will still give a higher value. And the reason the reason why this happens is because we made a big assumption here. What assumption have we made? Independence. Independence in what here? In terms of what?
Models?
Yeah. A bit more than that. Like and yes, exactly. Independence in models and also in the performance of the models. But you're right, especially in the models actually, because the way these functions work, they have to make independent decisions from each other. They cannot be correlated. When one of them is wrong, you're hoping that the other one is not wrong on exactly the same examples. Like you are hoping the other one makes different mistakes, same number of mistakes, but a different ones. If that makes sense, it will be wrong on a different set of cases. Then that's why the ensemble would give you higher performance. It was the same with the story with the prices. So, people made different predictions, but some of them would predict a lower price, some would predict a higher price. But you were not hoping that all of them would on average, give you a lower prediction in general. So, yeah. Okay. So going back to the slides. So how do we create these kinds of ensembles, like even in our exercise? How do we get them in practice? So the one way to do it is to train on different training sets. So we have our data set, and one thing we can do. We've seen even in the first lecture how we do cross validation. We split it into 10, for example, 10 chunks or 5 chunks, and we can train on those. Another way to do it is to do bootstrap sampling. So we have a data set of 100 data points, and we take some out, but some we decide to put back. So we sample with replacement. So what this means is that we sometimes can sample the same data point twice, and we take a different one out instead, or we just again we sample some data points twice or 3 times and so on. So with
is
replacement,
we keep a certain, we take one sample and say 50% of this we're going to put back for each one, just to make sure that they each have like 50% of the same samples about.
roughly, actually, that's a different way to do it. But let me show you that's a different kind of approach. Let me show you what normally people refer to when they talk about sampling with replacement. It's like you have, let me do this. So you have a set of a cross, a square, and a circle. 3 elements you have. When you sample with replacement, what it means is that you create a new data set, but now, so you start sampling with replacement. You sample one of them, for example. You sample, let's say first the square. You sample the square. Without replacement means that once you sample the square, you take it out from here. And next time you sample, you only have to choose between the remaining elements. That's what people mean when you sample without replacement. So now, and the next time I decide to sample the circle, and I take it out from here, I do not replace it. I do not replace it back in the original data set. Does everyone understand this? Sampling with replacement and without replacement? So when we we had this initially. So when we sample without, again, I'll say it one more time. When we sample without replacement, it means we sample for example, the square, but we take it out from the original set. So we do not replace it back. With replacement means we sample it and in the new data set, and we also put it back. And what happens when you do sampling with replacement, which is referred to on the first bullet point on the slide on the right hand side, is that you replace it back, and you can sample it again if next time you have a chance. Next time you have a chance of also sampling again the square, and maybe you also sample the circle, and maybe sample the x, and maybe you sample the square again. You can sample it's always probabilistic how you do this, but you can get it multiple times in the resampled case. Okay, so this is how we create a bootstrap sample with replacement. Some data points will appear twice or multiple times in the new data set. You can do cross-validation sampling, where we were talking about. We can reweight the data and with boosting, and we'll see that shortly. So, and we can also use different features. So now you don't sample the whole data point, but you can choose to only sample certain features. Maybe if the points have 5 features, you have people, and you have their height, their other things, their age, and so on. So those will be features. You can choose to only work with age now, and maybe with height in the next iteration, and so on. So how do ensemble methods predict? So we've seen an example with majority voting here, with on the blackboard with. So you have an ensemble of methods, and you can do majority voting with that. You can do this in an unweighted way, or you can also weight the vote, and you can weight the vote maybe based on how good the method is, like how well it can predict. That's one way to weight it. Or another way to even do it is to cascade. And here, cascade, what it means is that you have a model that gives you an output from input to output, and then that output from the first model, you pass it as an input to the next model. So you have a cascade. So you have one model that gives an output, and then you pass it as an input to the second model. And the output of the second model, you pass it as an input to the third model, and so on. So you have a series of models that can make sequential predictions. And this cascading is actually used, well, for example, even this idea is prevalent a lot in neural networks where they have layers, because each layer is a function that gives you some outputs, and those are passed as an input to the next layer, and so on and so on. So that's sort of like it can be seen as a cascade as well. So boosting is another approach in which you can combine multiple learning algorithms, and you basically create a set of classifiers, and they predict with a particular vote. So each classifier makes predictions, but you also weight these predictions. So you weight the classifiers and the predictions they make. This is what boosting does. You have a set of classifiers, and each classifier has a weight, and all those weights have to sum to 1. But this way you can weight multiple of them. And of course, you want to get sample diversity. So you want to classify a set to be diverse, to make diverse predictions, because we saw how if these are correlated, if the predictions are highly correlated, then this won't work. So you need diversity in the classifiers for this to be able to work. So you can upweight and we'll see how actually in boosting also the examples are also weighted, not just the classifier. So the examples get a weight also, and we'll see how some hard to predict examples are upweighted, and the easy examples are downweighted. Let's see some examples. Let's see some visualizations. So assume you have this data set with 4 data points, 3 pluses and a minus. Actually, here, look here. No, not there. So this is the 4 data. This data set with the 4. Now you have a set of models that can only make straight line boundaries. So you have one model that, for example, does this kind of prediction. So these ones are predicted correctly. So this one is plus, the red is a minus, but you see this one will make an error when it predicts this plus, for example, this particular model, this first model. Let me show for people on Zoom as well. Yeah, so here we'll have an error in the first classifier. In the second classifier, we'll have a different classifier D2, a different decision boundary that makes it like this. So then this one will make an error in this particular data point. But the thing is, when we combine D1 and D2, we get this. So then, yeah.
Between D1 and D2, when you say upward error, so we saw that one of the data points that we made an error on in D1, we increased the weight that we assigned.
Exactly.
Since D2 is now essentially corrected it.
Exactly. So what happened here, and I didn't get to that, yes. We, in order to get D2, what we did is that we have this sample and we upweight we increase the weight of that particular sample. So then when we train the same family of models again, it will find a different boundary instead, and we'll do this boundary. And now this one because it had a higher weight, now it's predicted correctly, but it made a mistake for this one. The next time we upweight also this one, and we combine the 2 classifiers to make this prediction. And now the final prediction will be correct. But we'll see how, because we'll have to. These classifiers will also have a weight, of course, and that's how we get this final prediction. And so here's another example, just to build a bit more intuition. So imagine you have this data set with the crosses and with green points, so reds and greens, and you have a decision boundary. So again, we were talking about how we can increase the weight of the data points. And one way, for example, to increase the weight, so you can increase it in some models. You can increase it easily by changing the loss function, but that's not always possible if you change the loss function. So what you can do instead is to actually duplicate them. So basically, these points that for which the classifier made a mistake. So look here. So there's these 3 reds for which the classifier made a mistake. There's another red here. So there's 4 reds and there's 2 greens for which the classifier made a mistake. So what we can do, we can duplicate them. So here. So now we have duplicated these points. Now we have two instances of each point in the same spot, and now that means that we essentially penalize the model even more when it makes a mistake for these data sets. And if you retrain the model on these additional weights, we'll see how it will change the boundary. So I'll show you soon how this new boundary will change. And
Would it probably shift down?
it will shift,
More
yes.
reds than greens, that way?
Yes. And it might even rotate. So this is one way we can increase the weight, for example, by duplicating the points. It's very easy. So this is a weak classifier we have, again, that classifies these points. Now it made 2 mistakes here and 1 mistake here. Now we increase the weights of those data points, of the blues and the reds. And you see now how, after we increase the weights, when we retrain, the boundary changes. And now we change to this one. So now it still makes 2 mistakes here, one here, but at least it's not the big ones that are highly weighted. And now we increase these weights because it made 2 mistakes. Those 2 mistakes. We also increase the weights for those 2, and we keep doing this. And now we found this boundary. And again, it's not perfect. This one has to, yes. But you see, this isn't linearly separable, this data set. But what happens is what you do at the end is that you combine all 3 boundaries. Remember, we had a boundary initially here, then here, then here. We combine all 3. And now, in this combined version, all the points are correctly classified when we do majority voting. Because this one was predicting reds, I think, only for the above. This one was predicting reds for the left, and this one is predicting reds for the left. And as a result, all the reds are correctly classified, and all the blues are correctly classified. So the question is, how much should the weights of the training examples change? We see how we increase these weights, the size of the blobs, and we increase the weights. How should we how much should we increase them? And in general, we'll assign half of the total weights to the misclassified examples. We have a total set of weights for all the points, and then at each iteration we take half of that and we assign it to the misclassified cases. And this is the principle in AdaBoost, how AdaBoost works. And it also has, we'll also weight each model by confidence factor alpha. So then models that have a lower error rate will have a higher confidence factor alpha. And I will continue next time for AdaBoost. But before then, any final questions for the last 1 minute? Any questions so far on this intuition? And yes, there is.
When you combine all 3 lines, isn't there like a bit of concern about like overfitting the data?
Yeah. You notice how when you combine multiple lines, the complexity of the model increases. So now with the combination of 3 models, we don't have a linear boundary anymore. You notice how this is a highly nonlinear. This is all correctly classified. So you can overfit, yes. But we'll see shortly that next lecture when we talk about AdaBoost. So this how we actually do implement it. That it won't overfit too much. There's something quite magical that happens in AdaBoost that it doesn't overfit, and we actually don't even understand even nowadays. Like it's an active research area, so we don't. Yeah. But there is possible potential to overfit. Yeah. Okay. I'll see you next week. You're welcome. Yeah. Not right now. I know I have several projects ongoing, but kind of tricky. Like unless the PhD students will would have something that they could help with. Like in that case, yes. But more bigger grant projects I don't have right now because I had like some 3 very good ideas, but I already assigned them to people. So if you're still like stuck, like send me an email again in like a few weeks, and if I think of something, I'll let you know.
I'm fine with like thesis or project. I'm fine with both thesis.
Both thesis and project. How much time are you able to dedicate?
So I'm planning for a 2-year master.
2-year masters?
So this is my first one.
Right. What's your sort of interest? What are you passionate about?